Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to Module 9 where we are going to study about earthquakes, focal mechanism and movement tensors. In the lecture 1 today, we are going to cover the concepts such as earthquakes and we will be focusing on elastic rebound theory. Then we will talk about seismic cycle that is associated with elastic rebound theory. Then we will have a brief overview of focal mechanism and we will see various types of fault geometries and the classification of the faults. So far we have studied about seismic waves in the previous module, and in the module that we are going to start with today, we are going to talk about the generation of the seismic waves. If you look at the seismic waves can be generated by many other phenomena apart from the earthquake. But the association of the seismology with the earthquakes is so strong that it has been viewed as the science of the earthquakes. In the lecture today, we will see the various kind of earthquake that has been generated by the faults, and those faults have their surface expressions onto the surface. And the earthquakes, for example, we have taken this earthquake, Turkey earthquake, which happened in 2023 with a magnitude of 7.8. You can see this earthquake has created a lot of devastation into the area. Even it has generated some fire, the secondary effect of the earthquake, and there has been a topple of the buildings under which many useful property and also the lives have been died. And this is an example of Bhuj earthquake happened in 2001 with a magnitude of 7.6, and it was found out that the earthquake happened due to a blind fault, which is quite unexpected. And this earthquake has incurred a lot of devastation into the area. Even there were several buildings that got toppled down, and it has taken a lot of lives into the area in that particular region of Gujarat. And this is an example of Sumatra earthquake, happened in 2004 of magnitude 9.1, and it also created a tsunami as well. And this is a very infamous earthquake which has taken a lot of life, and there was a lot of devastation into the property as well. And this is the recent one in Japan 2011 of magnitude 9, and which has also created a tsunami, and you can see it has generated a fire because of which a lot of people died, and it has basically done a lot of devastation into the area. This is an example of Kaikoura earthquake, and if you look at this picture, this earthquake has its surface expression. Not always all the earthquakes have their surface expression. A few does have. So this is one of them, and it has you can see has a fault scarp onto the surface, and this scarp is basically due to the relative movement of the plates during the earthquake. And this earthquake was of magnitude 7.8 and happened in South Island of New Zealand. And these are some of the major earthquakes happened in India starting from the year 1905, and you can see the locations are being shown by the small red colored dots, and these are mostly happening along the Himalayan boundary. And you can see, for example, the Kangra earthquake that occurred in 1905 due to the magnitude 7.8. Then there is a Bihar earthquake in 1934, and there is Assam earthquake that happened in 1950 of magnitude 8.6, and after that we saw Kinnor earthquake in 1975, and there is Uttarkashi earthquake, and there is Latur earthquake onto the Deccan Plateau, and there is this Gujarat earthquake that we just talked about, happened in 2001, which has basically claimed a lot of lives. And then there is Kashmir earthquake of magnitude 7.6, October 8, 2005, and there is Nepal earthquake recently happened of magnitude 7.8. And before we go into understanding the generation of seismic waves, we must need to talk about elastic rebound theory. And if you go into the history, then there was an earthquake happened on a fault, which is a very famous fault named as San Andreas Fault. And in 1906, there was an earthquake happened on it, which is a California 1906 earthquake. And this earthquake has claimed a lot of lives into the area, and a systematic understanding of this earthquake was required, because of which the American government has set up a committee of the expert scientists to understand the phenomena of this earthquake. While understanding this earthquake phenomena, there was a scientist with the name of H. Reed. He proposed a theory known as elastic rebound theory of the earthquakes on a fault. And as per this theory, the material at a distance on opposite side of a fault, if you look at the example here shown in this diagram, then there is this fault over here, and the material on both sides of the fault initially was moving up in the opposite direction relative to each other, but the friction at nearby the fault location is keeping them locked and preventing it from slipping. But after some time, when there is enough strain has been accumulated and the rock is no more able to bear that strain, and the strain accumulated gone beyond the elastic limit of the rocks, then fault start to slip and it result in an earthquake. So you can see in the second picture, the fault is basically keep on accumulating the energy, and at a point when this energy or the strain gone beyond the elastic limit of the rocks near to the fault, then the fault slips away, and because of the slipping, a high amount of energy in the form of earthquake releases. So in the third figure, you can see there is the slip already happened, and the fence over here, those which were once linear, are now having some offset. That is because of the earthquake that has created this offset along this fence. And this particular theory was considered to be a major conceptual breakthrough, because the fault has used to be seen the result of an basically earthquake, but the fault itself is the cause of an earthquake. So this was the misconception previously, that fault that is seen onto the surface, this for example this one, is due to the result of an earthquake. This was the previous misconception. But after this major conceptual breakthrough in the form of elastic rebound theory happened, then it was understood that the fault is itself the cause of an earthquake. Using elastic rebound theory, we think of them as reflecting the most dramatic part of a process called seismic cycle, which takes place on the segment of plate boundary over 100 to 1000 of years. During the interseismic stage, which basically consists of most of the cycle, steady motion occurs away from the fault, but the fault itself is locked, although some seismic creep can also occur on it. So this is the flow of the seismic cycle that happened during the elastic rebound theory. The first stage in seismic cycle is interseismic stage. Second stage is pre-seismic stage, which is just before the earthquake, and the co-seismic stage when the earthquake itself happens, and the post-seismic stage, that is the stage after the earthquake when aftershocks occurs. If we talk about the interseismic stage, this takes the longest period of time in the seismic cycle, during which elastic strain accumulates, and that occurs on a very bigger region. And in the pre-seismic stage, that is the stage just before the co-seismic phase when the earthquake happens. And in the pre-seismic stage, the foreshocks or the small earthquake happens, and these are basically known as the precursory effect of an earthquake. And thereafter, the co-seismic phase occurs. In this particular phase, the rapid motion of the fault generates earthquake, which produces seismic waves. Thereafter, the post-seismic phase happens. That basically is the responsible for the occurrence of the aftershocks, and the transient afterslip occurs for a period of years before the fault settles into its STG interseismic behavior again. So this cycle keep on going on, and this cycle generally takes 100 to 1000 of years. And if in order to understand this entire cycle, you will have to go through many number of faults, so that you can keep the different part of this elastic rebound theory together to have a clear understanding of the seismic cycle. So it is very important to have a good understanding of the seismic cycle, because it takes a lot of time, sometimes 100 or 1000 of years, which is not sufficient for a human life. So you need to study it in part along different faults. And this is just a graphical view of the elastic rebound theory. This is where the nucleation happens. This is the post-seismic phase after the co-seismic phase occurs, and this is the interseismic stage, which takes the most of the time of the entire seismic cycle. And during the co-seismic phase, the permanent deformation occurs, and this permanent deformation leads to the generation of high amount of strain energy. So during these few seconds, meters of the slip on the fault catch up with the few millimeter per year of motion that occurs over hundreds of years away from the fault. And now the question comes, why to study earthquakes? And the answer is, the earthquake study reflects the motion of lithospheric plates and may provide important information how and why plates move. And also it provides a good understanding about the fundamental physics of the earthquakes, faulting, and large-scale geological processes causing earthquakes. And using these 2 points, we can have knowledge of the earthquake, so that we can have construction that can be resilient to the devastating effect of the earthquake, so that we can mitigate the risk that is posed by the earthquakes. And now let's start with the focal mechanism. First, we will go through the fault geometry. And in order to understand the geometry of a fault, we need to assume that the fault plane is planar, or you can say the fault surface is planar, across which the relative motion occurred during an earthquake. And this is a typical example of the fault scarp near Crowley Lake in California, and this is along the most famous San Andreas transform plate boundary. And you can see there is this scarp here, this one along the fault that is basically passing through the Crowley Lake in California. And going to understand the geometry of many such faults that are responsible for the big or smaller earthquake all around the globe. And the geological observation of the fault that reach the surface show that this is often approximately the case, although complexities are common. So whenever we are considering the fault surface is planar, these observations are considered to be approximately correct, but not always this is true, but there might be some complexities that are basically common. And here is one of the fault geometry. You can see there is this stratigraphy, and there is a fault surface along this. This is the fault plane here, which is perpendicular to the plane of your screen. And this fault plane is basically we need to define by some parameters such as strike, slip angle, dip angle, etc. And that we are going to do in the following slides. And thus the fault geometry is described in terms of orientation of the fault plane and the direction of slip along the plane. And if suppose there is this block of plate, this is the entire block, and there are the stresses that are being applied, then due to the stress, the strain will accumulate, and at a point when strain energy will go beyond the elastic limit of the rocks within this block, then at a point the fault plane will be created, or you can say the slip along the fault plane will happen. So you can see there is this hanging wall, there is this football, and due to the stress, this hanging wall is having a slip in the downward direction in comparison to the foot wall, and you can see the slip is going in this direction along the fault plane. This is the fault plane, and after the fault has been slipped, so this will create this fault scarp. Now, thus the fault geometry is described in the terms of the orientation of the fault plane and the direction of the slip along the plane, and you can see this is the figure that depicts the fault geometry used in the earthquake studies. There is a coordinate system x1, x2 and x3. So this is x1 direction here, and there you have this x2 direction, and this is your x3 direction. And using this coordinate system, we are going to define some of the angles and the directions, such as the strike angle, dip angle, slip angle. And this block is basically the foot wall block, and here you can see this is the fault plane, and along which the slip is happening in this direction. And the fault plane is characterized by a unit vector that is known as the normal vector to the fault plane. So this is here the normal vector you can see, and the direction of motion is being represented by the unit vector d cap or d hat, the slip vector in the fault plane. The slip vector indicates the direction in which the upper side of the fault is the fault known as the hanging wall or the hanging wall block moved with respect to the lower side, the foot wall block. So in this case, the hanging wall is moving in this direction. This is the slip direction, and it is represented by a unit vector d cap, which is generally measured from x1 direction in the anti-clockwise direction. Similarly, there is a angle known as dip angle, which basically tell us about the amount of the dip the fault surface has, and that is generally measured from x2 direction in the anti-clockwise direction from the x2 direction, or you can say it is from minus x2 direction in the anti-clockwise direction. So the one thing that you must remember, because the x1 axis could be defined in two directions, so this axis can be this direction or can be this direction. So it can be 180 degree or maybe 0 degree. So it should be chosen so that the dip measured from the minus x2 axis is less than 90 degree. So in this case, if we are taking this axis in this direction, then only in the anti-clockwise direction the slip angle will be less than 90 degree. If you are going to choose this direction, then what will happen? This will be the direction, and you will end up having your slip angle more than 90 degree. So that is why we have chosen this x1 direction, this in this particular direction. Now let's read out what is written here. The x1 axis is in the fault strike direction. So this is the strike direction here, where the fault surface fault plane is meeting onto the surface, or you can say it is the intersection of the fault plane onto the surface. So that will give you the strike direction, and so this is what it is. The x1 axis is in the fault strike direction, the intersection of the fault plane with the earth's surface. The x3 axis point upward, this is the x3 axis, and the x2 axis is perpendicular to both of the two. So this is your x2 axis. The dip angle delta, this is the dip angle here. Delta gives the orientation of the fault plane with respect to the surface. So this is always in anti-clockwise direction, or you can say counter-clockwise direction. Because the x1 axis could be defined in two directions, 180 degree apart, it is chosen so that the dip measured from the minus x2 axis is less than 90 degree. And the direction of the motion is represented by slip angle lambda. So this is your slip angle lambda, and measured counterclockwise in the fault plane from the x1 direction. So this is your x1 direction here, and it is measured in counterclockwise, which gives the motion of the hanging wall block. So it basically indicate towards the hanging wall block motion that is onto this surface and with respect to the football block. The fault strike phi f, this is your fault strike, is measured in clockwise direction, and it defined as the angle in the plane of the earth's surface measured clockwise from the north. So it is always measured from the north direction. So this is your north direction here, and in the clockwise direction it will be measured like this from the strike direction. So this is what it is represented. So far we have been talking about x1, x2 and x3 axis, but you can also have your coordinate system in the geographical coordinate system. The orientation of the fault and the slip can be described by giving the normal and the slip vector with x cap in the north. We can have x cap in the north direction, y unit vector in the west direction, z cap pointing upward. And if we do so, then in that case the normal unit vector to the fault plane may be represented by this particular matrix, and the slip vector, a unit vector in the slip direction, can be represented by this particular matrix. And now let's talk about the classification of the fault and on the fault geometry. If we take the pure strike slip fault, in the pure strike slip fault, the two blocks move side by side with respect to each other. It doesn't have any slip along the dip direction. Okay, so there are these two blocks you can see, and these are moving relative to each other side by side. Okay, so likewise there is another possibility. These two blocks are again moving side by side but in opposite direction to the first one. So this particular fault known as the left lateral strike slip fault, and this is the right lateral strike slip fault. So how do you identify which one is the left lateral and which one is the right lateral? If suppose imagine yourself onto one block, let's suppose we are on the top of this particular block here. Let's suppose I am standing over here. Okay, and I am standing over here onto this block and looking at this particular block here, this one. That is just opposite away from the fault boundary. That is, you can say over here you are just looking onto the other block. If it appears to be moving in the left direction, then it is your left lateral strike slip fault. If it appears moving in the right direction, then it is your right lateral strike slip fault. So in this case, if you are standing over here and looking at this particular block, then you will see that this block is moving in the left direction because this arrow is indicating the motion here. Okay, so that is why if you are even standing onto this block and looking at this block, then you will see that this is moving in the left direction again. So this is your left lateral strike slip fault, and your slip angle, since the motion is happening along the strike, and we need to measure our slip angle with respect to the x1 axis, you can see, and the motion is happening in this direction, so the lambda will be 0. So in this case lambda is 0 degree. Likewise, if you are standing over here and looking at this block, you will see that the block is moving in the right direction. Then it is your right lateral strike slip fault. In this case lambda will be 180 degree. So this is what it is written. When lambda is equal to 0 degree, the hanging wall block moves to the right and the motion is called left lateral. Similarly, for lambda is equal to 180 degree, right lateral motion occurs. So this is your strike slip fault. This is just an animation taken from Iris, and you can see that this is a pure strike slip fault, and you can see the one block, the hanging block, is moving into the left side, so it is a left lateral strike slip fault. Why I am saying that? If suppose you are standing over here, you can see this block, you can see that it is moving in the left direction with respect to you. So it is your left lateral strike slip fault, strike slip pure fault, pure strike slip fault. And in case of then there is second category of dip slip fault. We are going to take the basic pure dip slip fault, and in this case the slip is happening in the direction of the dip. So it is happening in the direction of the dip. Then what is, so let's look at this one. So what you will observe that the hanging wall is moving in the down direction. So that is your normal dip slip fault. So in the normal dip slip fault, the hanging wall moves in the downward direction relative to the foot wall block. So in this case, the slip angle will be your 270 degree, because if you look at this geometry, so your hanging wall is moving in this direction. Okay, and you need to measure your slip angle in the anti-clockwise direction. So from x1, so it will be like this. So this is your 270 degree. So this is what it is here. Lambda is equal to 270 degree. The hanging wall slides downward, causing normal faulting. So this is just an animation taken from USGS, and you can see that the hanging block is going in the dip direction. This is a pure dip slip fault. Likewise, if you look at another possibility of the dip slip fault, that is a reverse dip slip fault, where the hanging block is moving in the upward direction. Like in this animation as well, which is taken from iris, the hanging wall is moving upward in this direction. So in this case, if you go through this fault geometry, the slip is happening along the dip in the upward direction like this. So in that case, your lambda will be up to here only. So in this case, lambda will be 90 degree. So lambda is 90 degree. And the hanging wall goes upward, yielding reverse or the thrust faulting. So dip slip fault, so basically the strike slip fault are of two types. One is the left lateral strike slip fault and the right lateral strike slip fault. Likewise, the dip slip faults are of two types. One is the normal fault, another one is the thrust fault or the reverse fault. So there are some points that we must remember about these focal mechanisms. Most earthquakes consist of some combination of these motions and have slip angles between these values. It is thus useful when thinking about earthquakes mechanisms to remember the three basic faults. The three basic faults are the normal fault, reverse fault, strike slip fault. Okay, and if we treat a fault as rectangular, the dimension along the strike is called the fault length, and the dimension in the dip direction is known as fault width. So this is an important concept. The dimension along the strike is known as fault length, and the dimension in the dip direction is known as fault width. The fault may curve and require a three-dimensional description. Rupture may occur over a long time and consist of several sub-events on different parts of the fault with different orientations. Such complicated seismic event, however, can be treated as a superposition of the simple events. Now let's have a summary of today's lecture. Elastic rebound theory states that strain accumulated in the rock is more than the rocks on the fault can withstand, and the fault slips, resulting in an earthquake. Pre-seismic stage that can be associated with a small earthquake, that is the foreshock. So that now we are talking about the seismic cycle. There is the stage that is known as inter-seismic stage, then we have pre-seismic stage, thereafter we have co-seismic phase, and then finally we have post-seismic phase. In the inter-seismic stage, the material on the both sides of the fault moves relatively in the opposite direction to each other and try to accumulate the stress or the strain. In the pre-seismic phase, this is just before the earthquake, and in this pre-seismic stage, the foreshocks happens. And the co-seismic stage, the earthquake itself happens, which basically marks the rapid motion on the fault and generates seismic waves. In the post-seismic phase, that occurs after the earthquake, and aftershocks and the transient aftershocks occur for a period of years. The two different coordinate system, phi s lambda and n cap, d cap, are useful to describe the fault geometry. In the case of geographical coordinate system, the unit vector to the fault plane can be described by this matrix, and in case of the same coordinate system, the slip vector is defined by this matrix. For pure strike slip fault, lambda is equal to 0 degree. The hanging wall moves to the right and the motion is called left lateral, and for lambda is equal to 180 degree, right lateral motion occurs. For pure dip slip fault, lambda is equal to 270 degree. The hanging wall slides downward, causing normal faulting, and lambda is equal to 90 degree, and the hanging wall goes upward, yielding reverse or the thrust faulting. And this is all for today's lecture. In the next lecture, we will be talking about the first motions, and these are the references. Thank you so much. Bye-bye.